professors to giving us two amazing talk. The first one, let's welcome Yoshihiro Kanamori from University of the Tsukuba. Our first talk is going to talk about image-based digital human. That our speaker is received the bachelor, master, and PhD degree from computer science in University of Tokyo. And before that, he was visiting researcher in the laboratory of the Marcus at ETH and also visiting University of Edinburgh. He served a lot of as a PC committees in top conference in the computer graphic area. Let's welcome our first guest. So I'm going to stop sharing the screen and moving to our first guest.
Yep, thank you very much. Okay. Can you see the screen?
Yes, that's good. I can see the screen now.
Okay, thank you very much. Thank you very much for the interaction, and thank you very much for organizing this wonderful webinar. My name is Yoshihiro Kanamori from the University of Tsukuba. Today, I'd like to introduce our research project about image-based digital human. So, first off, let me briefly introduce myself. I earned my PhD in 2009 under the supervision of Professor Tomoyuki Nishita, who is a pioneer in computer graphics in Japan. From 2014 to 2016, I conducted research under Professor Marcus Gross at ETH Zurich, a world-renowned expert in the computer graphics field. I am currently a professor at the University of Tsukuba. I run our laboratory together with Associate Professor Yuki Endo, who was once my student and is now an outstanding researcher. Professor Endo appeared in the geographics webinar 3 years ago, and he was still an assistant professor. So please check it out if you are interested. Our laboratory currently has 4 doctoral students, 5 master's students, and 3 undergraduate students. Regarding my research journey, until 2009, during my time at the University of Tokyo, I was interested in real-time rendering under interactive simulation. After joining the University of Tsukuba in 2009, I began working on computer graphics using single images as input. Furthermore, around 2017, when Professor Endo joined our laboratory, we started working on deep learning. Then, since 2018, around 2018, prompted by joint research with industry, we have been engaged in research on digital human. So let me introduce our research motivations. There are 2 main directions. Primarily, we develop technologies for novice users based on single image input. This aim is to democratize photorealistic computer graphics. The other is professional 3D computer graphics research for industry. We mainly promote joint research with domestic companies. To date, we have collaborated with well-known Japanese companies as shown below. Here are some projects from our laboratory. Our research themes cover a wide range of topics. The top left research, this one, involves restoring high dynamic range images from a single low dynamic range image. We were the first to apply deep learning to this task, achieving a dramatic improvement in performance. The middle top research involves relighting portrait images. We'll cover this in more detail later. The top right research generates cinemagraphs from a single landscape image. It's astonishing how much more impressive videos can now be created using video generation AI. The bottom left research uses satellite data to recreate seasonal changes in mountainous terrain over a year. The bottom right research improves the image aesthetics, and it's the first study to consider 3D perspective in this context. Next, I'll introduce our research on image-based digital humans, which is today's main topic. We were working on various projects in this area, but due to the time constraints, we'll highlight a few selected ones today. First, I present our research on relighting full-body human images, this one. Relighting of portrait images is a task of altering shadows or shading after photographing a person. It has long been studied in the fields of computer graphics and computer vision. Much of this research focuses on facial images with various applications such as post-processing of portrait images. For faces, simplified problem formulation has been used. That is, since faces are largely convex shapes, light is not blocked or occluded around the face. This significantly eased the problem. However, when targeting the entire human body, as in our research, the shape is no longer convex. Light is occluded everywhere, and realistic shading or shadows cannot be achieved without accounting for light occlusion. So we proposed single image human relighting with occlusion, light occlusion. So we pioneered single image full body relighting, which was published in Geographic Asia 2018. From this input image with a binary mask indicating the human figure, we conduct inverse relighting to estimate geometry dependent shading and texture. Texture and light information. And after switching the light with a new one, we can relight the human figure in the new lighting environment. So after our project, there have been proposed follow-up studies because our first work was for diffuse reflection only, and trained only with computer graphics data, so the appearance was a bit synthetic. So we extended this first work to handle non-diffuse, reflection, to handle reflection, and conducted a domain adaptation to handle real images with my student. And after this, very powerful research teams like in computer Google or Meta tackled, or NVIDIA tackled relighting of high quality human images using light to stage data. One light at a time data. So the results were really amazing. So I asked myself, without light stage, should we discontinue our research? But after several discussions with my student, we found that the previous methods, our follow-up studies cannot handle high frequency shadows. As you can see, shadows are blurred. So that is the point we tackled. So this is our latest work, which was published in Eurographics this year. So we explicitly modeled the light occlusion to handle all frequency shadows. So from this input image, we again apply inverse rendering to infer materials, including specular component, and also geometry like depth map and normal maps. So we conduct shading, physically based shading. So this, you can see the comparison with the previous work conducted by Google research team. So you can see a sharp shadow here and highlight here. But yeah, in their results, you can see how the shadows or highlights like ours. Okay, so there are several technical challenges. The first one is that current trend of photorealistic relighting is to handle geometric aware shading. And I mean, for shading and shadows, geometry seems important. Yeah, that might be kind of a common sense for 3D rendering, but yeah, nowadays relighting techniques, use explicit geometry. So one example is proposed by G et al. In their method, from this input image, they explicitly reconstruct the 3D shape of the human body, then conducted ray tracing to output this kind of image. But 3D reconstruction and ray tracing are both very slow, and if this 3D reconstruction has some error, the error accumulates in the final outputs. And even worse, the output is only for diffuse. Contrarily, our method can reconstruct or infer geometry and material and conduct physically based lighting, including specular reflection. So we can achieve fast and simultaneous material and geometry optimization. The second challenge is that hard shadows require explicit modeling strong lights. So typical previous work use light as this kind of low resolution environment map. So because the lighting information is very low resolution, they cannot capture strong lights. So the output, in the output images, the shadows and shadings are very blurry, like this. In our method, we explicitly find the strong lights as directional lights. Then we can get this kind of strong lights. But by explicitly capturing strong lights, we can handle hard shadows like this. So this is the third challenge. We also represent soft shadows. Soft shadows to represent all frequency shadows. I mean, from the hard to soft shadows. In the context of real-time rendering, there have been proposed several methods to handle real-time soft shadows like this. But these techniques for real-time rendering, so they are not for differentiable techniques that cannot be integrated in the modern deep learning pipelines. So we extend the directional light approximation to with a area light extension, and extend the algorithm to handle differentiable soft shadows. So this way we can handle soft shadows as well to achieve all frequency shadows. Okay, that's it. So let me show some example in the video. So maybe here. This is an example with a real image. So the rightmost example is our result. You can see the hard shadows around the arm. You can also see the highlight Yeah, like this. Okay, that's it. Then next topic is body reshaping and reposing of human images. So let me begin with the background. Techniques for editing the poses and body shapes of portrait images is useful for virtual fashion shooting and diet simulations, as shown in the images below. So for body pose editing, there are several methods from this kind of input image and pose information. We can change the pose, but in the previous methods, the output faces are often distorted, or the facial identity is not maintained, and clothing features are also changed. In body reshaping, previous techniques often used image warping using flow fields. So using flow fields, unfortunately, they cannot change the body shape a lot. I mean, only a small distortion is allowed. Otherwise, the body shape will be heavily distorted. So this is our method. Previous methods only handle either one, pose reshaping or reposing only. But our method can handle both. So our method is the first attempt to edit both pose and body shapes simultaneously, and preserves facial and clothing features of the input person. Our inputs are as follows: this input image and pose information, and body shape information such as height and weight. We can synthesize like this. Let me introduce some key ideas. So in 3D computer graphics, body shape and pose can be edited quite easily if we know the explicit body shape. So our idea is to use a 3D body shape model. This is a very famous 3D model called Simple X model to drive body reshaping and posing. So this is the pipeline. This page explains the pipeline of a method. With this input image, we fit a simple X model, body shape model like this, and we project the input image as a texture to obtain this kind of textured human body. And from these pose and body shape information, we mimic or tune the simple X parameters to change the pose and body shape like this. But in this result, you can see the hand texture is bound onto the pants, and the face is very distorted. So we apply diffusion model to refine the output image like this. I think most of the audience knows diffusion model, but let me briefly introduce diffusion model. In the stable diffusion framework, UNet is trying to reconstruct an input image from noise like this. So what we do here is to refine the distorted region selectively. So, this is the reposed and reshaped body image, and we can specify which part is distorted or with artifacts by detecting the occluded regions. This mask white and black white regions indicate the occluded regions in the input image. So with this mask information, we selectively refine the distorted artifact regions, like we refine them like this. But yeah, for refinement, finding optimal noise is not straightforward because the optimal noise strength differs depending on the input images. For example, for this input image, we add noise with the strength 10%, 50%, 90%. The results are very different. For example, with 10%, the reconstruction is not enough. 90% is too strong. And in this case, 50 seems optimal. But if we focus on faces, 50 is not enough for face. And yeah, with 90, the identity, facial identity is almost lost. And yeah, this is the same for human image computer graphics images. So with strength 50%, the outputs are again distorted. Yeah. So instead of finding optimal noise strengths, our strategy is to iteratively refine with weak noise. So like this, we add 30% noise and denoise, and we get this. And again, we add 30% noise and denoise we iterate this procedure. By doing this, we can keep the basic structure of the target image while we can refine the details progressively. So we apply this procedure for the whole body first, and then refine the face in the second step. Okay, this page shows the qualitative comparison. The leftmost one is the input image, and the rightmost one is the result. So if we notice the clauses, the results of previous methods have unnatural texture. In this result, the clause are changed. Yeah, this is terrible. The overall appearance has been changed. But our result is very realistic. If we notice the faces, we have the same conclusion. The results in the faces in the previous methods are implausible, but our face is very plausible. And as I said, our method is the first attempt to handle both body shape and pose editing. So from this input image, we can change the body shape and pose simultaneously like this. Yeah. Okay, that is for this part. So the third one, this is the last topic, makeup manipulation. This research on makeup manipulation was conducted by Dr. Shinshao Yan, a researcher at our collaborative institution company. He was a doctoral student in our laboratory until last year. Let me explain the motivation for this research. Makeup is essential for digital characters, especially female characters. However, preparing makeup for digital characters is challenging. For example, manually creating makeup or measuring real-world makeup is extremely time-consuming. So we propose the first attempt to extract makeup from images, not 3D for 3D faces. From this kind of input images with makeup, we extract makeup information as a UV map, texture representation for 3D avatars. So in this makeup, skin color and lighting effects are excluded. So we can reuse this makeup information for any 3D avatars like this. So yeah. So this research is based on the 3D morphable model or 3D MM. 3D MM is a parametric head model with shape, pose, and expression parameters. Maybe most of the audience knows, but yeah, Flame is a Flame model is the and its variants as the de facto standard of 3D morphable models. And the 3D morphable models are often used for 3D recovery via fitting to the, for example, images like this. So our model often use this framework. Our method is composed of three steps. The first step is coarse reconstruction. From this input image, we apply a neural network for inverse rendering to extract 3D shape of the human face and materials like diffuse albedo, specular albedo, and normals, and like this. Like this. And in the second stage, second step, we refine the first stage outcome. So because the first stage is just for coarse reconstruction, the output might have missing regions like this. So we first complete or in-paint the missing regions using a neural network like this. And then we conduct optimization to refine the extracted coarse materials. So in the diffuse albedo, we assume it includes makeup information. In other words, we assume makeup are only diffuse, but in the real world, makeup has specular components. So in future work, we would like to handle specular components of makeup, but yeah, in this work, yeah, as I said, we assume the makeup are only diffuse. So from this diffuse component, we extract their skin, skin image, skin texture without makeup and makeup information, and alpha matte to blend the makeup and the bare skin image to reconstruct the diffuse albedo. Yeah. So after this decomposition, we can reconstruct face images with several components. For example, from this input image, we can fully reconstruct the face like this. And if we map the textures onto the 3D MM, it looks like this. And if we overlay the 3D reconstructed face with bare skin only, it looks like this. So yeah, she looks like, she looks without makeup. And we can add makeup like this, and we also reconstruct with bare skin and lighting without makeup. So yeah, this makeup extraction has several applications. So the first application is makeup transfer for 3D faces. This is the main motivation of our research. And we can interpolate the makeup. This is this has almost no makeup, and this is fully, with the full makeup, and we can change the writing. And we can also transfer makeup from images, 2D images to 3D images. The facial part is represented as 3D morpho model, so we can simulate 2D to 2D. Actually, this is 2D to 3D makeup transfer. After constructing makeup textures, we can construct a statistical model of makeup. Because makeup data aligned in pixel-wise in the UV space, we can apply principal component analysis to the set of makeup data. Then we can sample from the statistical model to various types of makeup data like this. Using this makeup statistical model, we can improve the 3D reconstruction with faces with makeup. So without statistical makeup model, this result cannot reconstruct realistic makeup like these lips, as you can see here. But in our results, the makeup are well reconstructed. So after this work, we also improved the initial work in two ways. We proposed two types of makeup prior models for more robust or efficient versions. The first version is principal component analysis version, which is 180 times faster. So that is very efficient. The other one is Style-Yan2 based. This is not so faster, just 3 times faster, but it can represent detailed and accurate makeup. So it has, similar applications, but much more higher speed or higher quality. Okay, this is the summary of my talk. Our laboratory is engaged in various digital human research projects. Today, we introduced 3 of them: rewriting full body human images, modifying body shape and pose, and manipulating makeup. Beyond this, we also working on projects like text-based virtual try-on, personalized facial age editing, human nerve from sparse views, and facial texture resolution. If you are interested, please access our website via the QR code. Looking ahead, we have 2 main directions. One is continuing to develop task-specific AI technologies for computer graphics, as we have done so far. The other one is developing and utilizing visual foundation models. That concludes my talk. Thank you very much for your time today.
Okay. Thank you very much for the talk. So is there any questions in the audience? Let's have a look. But I have a question at first. Because most of your work is from one image based, which is slightly different from computer graphic traditional pipeline. So how do you see in the future, like this, like a computer graphic pipeline, will this be replaced by the computer vision or AI GC? How would you say? Because AI has developed so fast and machine learning stuff goes so fast, will this be like replace the whole computer graphic pipeline, like a 3D modeling, those things?
Thank you very much for the your question. it's a bit difficult to answer. Obviously, the current trend is to integrate the AI technologies to traditional computer graphics, and one possible or one promising direction is to infer personalized computer graphics just from one or few images. But predicting further directions a bit difficult for me. Is it answer?
Yes.
Does this answer your question?
Yes, that answers my question. Okay. Thank you very
Thank you.
much for your talk. I think we are going to move on to the next guest. Again, thank you for